So our next speaker is Professor Samir Shende. He has helped develop the Tau performance system, the program database toolkit, and the extreme scale scientific software stack with G4S and the HPC Linux distro. His research interests include tools and techniques for performance instrumentation, measurement, analysis, runtime systems, etc. He serves as a research associate professor and the director of the Performance Research Lab at the University of Oregon, and as the president and director of the Paratools. And as I indicated in my talk, we have been working very closely with Professor Shende's team to have a very tight integration of the MVAPICH2, the MPIT functionality, and also with the Tau to carry out extreme scale performance engineering. And that's what Professor Shende will be talking. So Professor Shende, please welcome. And you can share your slides and get started.
Thank you very much for inviting me. And I will share my slides now. Is it okay to share?
Should be coming. I think not yet. Stop.
Is this okay?
Yeah, it is coming up. Yes.
Okay. So thank you again for inviting me for this talk on performance engineering using MVAPICH and Tau. I will introduce the core concepts of Tau and MVAPICH functionality and describe the tools interface and how we have integrated the two tools. I would like to first thank the MVAPICH2 team at the Ohio State University and the Tau team at the University of Oregon. The MVAPICH2 project, as you all know, is a high-performance open-source MPI library which has been available for download in open-source form, and it has over 20 years of history and over 1.4 million downloads from the Ohio State University site, and it empowers many of the top 500 clusters. The Tau performance system is a comprehensive profiling and tracing toolkit that aims to provide portable profiling and tracing capability across different parallel programming and execution paradigms. It has three components: the instrumentation component, the measurement, and then the analysis or visualization. Its key strength is that it's widely ported to many different platforms. It has an open source BSD style license, and it can operate very well with MPI, in particular with MVAPICH2, and it integrates with application frameworks. So in case you're wondering what Tau can provide, it can show you how much time was being spent in different code regions of the application, at the routine level, outer loop level, even within the loops at the statement level. And it can do this for application code, libraries, and it can show you in great detail of where your application is spending its time. And instead of time, you can substitute it with the hardware performance counters for packages such as your Liquid, which can then show you floating point instructions, data cache misses, branches taken, memory usage of the code. You can even see the high water mark of the total memory use. And I mean the stat, E, text, data, BSS, all of it. You can see exactly how much your application process took. You can see
Samir,
the characteristics.
Samir, your voice is fluctuating a little bit.
Is this
voice...
better?
Yes.
Okay.
This is better.
You can see the I/O characteristics of the code. You can see the contribution of each phase of your application, even scalability. And with MPI, you can ask questions like, how can I tune MPI for better performance? What performance variables, what control variables does the MPI runtime, like MVAPICH2 export, so I can observe and control its performance. So as I mentioned, there are three different components: instrumentation, measurement, and analysis, where you can add hooks to your code. You can perform measurements such as profiling and tracing, and then you can analyze the data that's generated using tools such as Paraprof or Vampire. Our goal is to support all the HPC platforms and compilers and runtime systems with no exceptions.
And in the instrumentation phase, we support a number of different languages, including Fortran, C++, Python, and support automatic instrumentation. We also have measurement and analysis support for different runtimes, including MPI, OpenSHMEM, DMAP, Eugenie, and pthreads, OpenMP. We use the OpenMP tools interface, and GPU runtimes, including CUDA, OpenCL, Level 0 for looking at Intel GPUs, DPC++, ROCm, OpenACC. We interface with other third-party libraries such as OTF2 and Scorpy, and support both direct and indirect performance measurement options, which includes adding probes to your code and also using sampling so you can interrupt the execution and then generate events at the timer level where you have begin and end events, or you can trigger an atomic event with some data value. And this is used in the performance variable tracking in MPIT. And with the entry and exit semantics, you can create exclusive and inclusive time or duration for your code and generate profiles which show you the aggregate data. So you can see how much time was spent in code regions, or traces which show you what happens when in along a timeline. So you have many different options for profiling, including flat profiles, call site profiles, all the way to traces. And you can use sampling or event-based sampling with interrupt that comes from the operating system, or when you get an overflow event of hardware performance counters. So you can see that based on the interrupts that you receive in your code, you can create an estimate. Tau creates an estimate of where it thinks the application is spending its time, but it can miss out some code regions between the interrupts. So we have instrumentation where you have start and stop hooks that are inserted at the entry and exit of routines. And this can track the time spent in the different code regions at a more fine granularity. It also uses throttling of lightweight routines so that you can control the overhead of instrumentation. And you can use both sampling as well as instrumentation together in Tau to create profile files, which can include flat profiles. It can include call path profiles that show you the time spent along a calling edge in a call graph. So in this case, if you see that you can see the time spent in MPI send when it was called by the function F2, by F1, by main, and you can set the call path depth environment variable or enable tracking of Tau call path using these environment variables. I'll cover these variables a little more in detail. You can set similarly a call site variable so you can see exactly which line of code a particular call comes from. And we have phase profile support as well in Tau. One of the popular ways of using Tau is to just track the time spent in different runtime systems, including MPI, where we can track with eMPI profiling interface as well as the MPI-T tools interface. Other runtimes like pthread, OpenMP, Intel Level 0, OpenACC, OpenCL, CUDA, ROCm, even the Cocos profiling API, where we can push and pop regions and observe the kernel execution times, and Python for AI and ML applications. We can look at the combination of different runtimes, including MPI with OpenMP or CUDA or Cocos. And we can add hooks to your code even at the source level using a tool called Program Database Toolkit, where we can parse the source code. So with Tau, you can add hooks to your code. With compilers, you can also use the preloading feature of Tau, where you can just preload a dynamic shared object. So without changing your application, you can just launch the application using a tool called tau exec. And you have to be careful that on Cray systems, you should link it with the dash dynamic flag so that it creates a dynamic executable if you wish to use the tau exec, which only works with dynamic executables. It works like this. You can launch your application with the tau exec-EBS or event-based sampling. And then you will get the time spent in MPI as well as get samples in the rest of the code. Then you can launch paraprof and view the data, or pprof. We have options for different GPU runtimes. As you can see, with tau exec, you can say ROCm or level 0, L0, kubectl, or OpenCL or OpenACC, or even track the I/O of the application using tau exec-IO, or OpenMP with the -OMPT. You can specify a specific configuration of tau when you have multiple of those installed, including OpenMP tools interface, OMPT, and enable event-based sampling even with other hardware performance counters, and specify a resolution like this. So that's an introduction on tau. To look at the performance of the MPI runtime in detail, we have the support of using tau and MVAPICH using the MPI tools interface. And in this case, we go beyond what the PMPI interface provides. The PMPI interface essentially allows you to just observe the time of the MPI call and see the parameters that are passing through the MPI call. But with MPI-T support, we can look at performance variables to track the inner workings of the MPI runtime and also control the different aspects of the MPI library using the control variables, or CVARs. They are variables for memory usage, InfiniBand, network, registration cache, shared memory, point-to-point messages, and even collective operations. So you can change the algorithm used inside MPI. And this is how you typically use the MPI tools interface. And this is done inside tau, so you don't need to do this programmatically. But we use the MPI tools interface to interface these two tools, and we can get the performance variables, create reports and recommendations. We can set the control variables. And here is an example of doing this in a non-interactive mode or a user interactive mode, or based on a policy where we can evaluate for different phases and reconfigure MVAPICH based on the performance data that's generated. And we have a performance measurement model which includes support for both enter-exit semantics as well as atomic operations. And we collect this data on a per thread of execution, and then we can get a view of the performance across the whole application based on these interval and atomic events. And then we have support for plugins in tau. So you can create multiple plugins. They can then be used for doing performance analysis, and they can observe the different events that take place through tau. So both event and trigger plugins are synchronous, and they are called directly from within the application. And with this plugin architecture, we can observe what's happening in the application without actually modifying the performance evaluation system. And we can create a user can create a different plugin and observe what happens in terms of events that pass through. It looks a bit like this. Here we have the MPI tools interface and MVAPICH and tau. And then you can have an auto-tuning plugin where we can specify the policies and create a recommendation. And you can customize this. You can look at the different states of your application and control the plugin based on regular expressions or control plugins. And we can create phase-based recommendations. So we can observe the timing inside MPI routines. We can look at other collective operations and give recommendations. For example, if it's spending too much time in collective operations, you could say, please consider offloading the computation using the sharp hardware offload protocol supported by MVAPICH 2. And here are recommendations that show up in the Paraprof browser, as you can see. And there are other variables that MPI MVAPICH supports, and this can include support for controlling the pool size of the communication buffers or VBuffs, and you can look at the thresholds that can be controlled to switch from an eager protocol to the rendezvous protocol. And to control all this, you just take your uninstrumented application. If you run it with, say, MPI run command, you can turn on tracking of MPIT performance variables when you have configured tau with the dash MPIT flag. And then you can set the control variables for the metrics and their values and just launch an uninstrumented binary with the tau exec specifying the MPIT tag. And you can have multiple tags during configuration. And then it will take these values and set those control variables internally inside tau. But what is important here is that you did not need to modify the binary in any way. Here are the pvars performance variables that are exposed by MVAPICH 2. It has a rich set. And I believe that MVAPICH 2 provides significantly more performance variables and the rich set of performance variables compared to other MPI runtimes. And you can see the control variables that are exposed in the Paraprof display and what they stand for. So you can see the detailed explanation for each control variable. And you can have arrays of control variables where you can specify one or more control variable metrics and their values like this. Here are examples of looking at the VBuff communication memory buffers. And you can control that, you can change the values, and you can see how the old and new values are maintained and how the memory usage can be controlled. For example, if you're not using a lot of the memory inside the MPI runtime, you want to give it to the application, you can change that number of VBuff pools. And then by setting those values, you can reduce the total amount of memory usage. We also have support for extending control variables on a per communicator basis. You can have a named communicator, a communicator that you name using the MPI com set name in the application, and then use that communicator name over here in this environment variable with MPIT, and then specify the control variable name and its value in this kind of a tuple, a set of tuples that you can specify. And here I have specified the name of a variable, a communicator, and I can track the time spent in MPI operations on a per communicator basis and also set the CVARs accordingly. This is used in code such as the comb application at LLNL, where you can change the values and you can see that it takes less time in this case. This is before and after the modification. And you can also see what's happening in the rest of the code. As I mentioned, we have support for event-based sampling. And that will show you the different code regions and where in the source code your application is spending its time, right down to the source level where you can see the header file and the line number that it's associated with. And these are the control variables that are exposed by MVAPICH 2 in this case. And you can see the values and the different values that you can set. This is on an IBM Power 9 system. We also have support for path-aware profiling in tau. So if you are sending a message where the memory resides on a GPU and you're sending a message to another node and you want to track how the message gets transferred from GPU A to GPU B to the network interface at the sending end, and then, right from the network interface down to GPU C to GPU D, and then residing in the shared memory, you can create this path-based profile in Tau by looking at the receive and send path IDs like these, and create profiles which show you a message MPI send operation partitioned by different messages, where the message path IDs are encoded in the path of the MPI send operation. We also have a 3D profile browser where you can view all this performance data in Tau. And then you can download Tau and Tau Commander tools from these URLs. We also have support for containers, and you can learn more about it in our extreme scale scientific software stack, where we have a number of different options, including virtual box images. We have stack-based recipes for installing Tau and other tools on bare metal, and also containerized distributions, including support for Docker, Singularity, as such, using extreme scale scientific software stack. And we also have an AWS image where we have MVAPICH X bundled with the support for EFA that Matt just described, and Singularity, Docker, Share, and other HPC container runtimes, along with SPAC and support for GPU runtimes as well. A lot of this work goes on at the Performance Research Lab in Oasis at the University of Oregon in Eugene. And I would like to thank our sponsors, including the Department of Energy, CEA France, Department of Defense, National Science Foundation, our industry partners, including Intel, NVIDIA, and Mellanox, AWS, AMD, Broadcom, IBM, Google, NASA, and our partners at different institutions, including the Ohio State University, Paratools Inc., the University of Tennessee, Knoxville, TU Dresden in Germany, and Jülich Supercomputing Center. I have a couple of different slides for reference here, and these slides are available on the web page. And you can see the different runtime environment variables that Tau provides support for. Now, to stay on track, I'll take questions, but I would like to thank the Exascale Computing Project for their sponsorship of the Tau project. Are there any questions that I can help answer?
Yeah, thanks, Amit. Thanks a lot for the overview. Are there any questions people have? They can post questions to the Q&A box or Slack.
Yeah, I have a question.
Go ahead.
Can Tau give us frequency of different message sizes for an ISIN, like a bucket kind of thing, like message size wise frequency?
So, Kaushik, we have had some options in Tau where we can control the buckets and partition the time spent in MPI operations based on different bucket sizes. I can discuss with you offline some of the early work that we have done in that. This was several years ago, but we can control the bucket size in that manner. Now, I'm talking about the synchronous MPI operations where we're just tracking the time spent in a particular operation. If you're interested in looking at the asynchronous part, then I think that's future work that we would probably need to work on. Did I answer your question?
Yeah, actually, I was talking about the different types of message sizes and how many times they were called, like, because Tau gives total count and average and mean and other statistics. But yeah, we can take it off.
I have a question.
Yes, of course.
Go ahead.
So what kind of information can we get from the Python applications, like particularly that are using the MPI for PY library?
Yes.
And, Python.
So for Python, we can see every entry and exit into Python routines. So you can see the Python file name, line number, and function name in Python. And we keep a consistent call stack. So you can see that this Python function called the the MPI call, and then you can see what happens inside MPI. You can also do event-based sampling. Now, instead of tau exec as the tool, you can just simply replace that with tau underscore Python as a tool. You need to configure tau with the dash Python options with the MPI, and then you will be able to see both Python as well as MPI timings. But remember that there is an overhead associated with every entry and exit tracking. So we have to be careful with adding too many options. Does that answer your question?
Yes, it answered my question. I have one more question on this. Like, do
Sure.
you support the Python layer? So basically, Python will be, some Python functions will be implemented in Python. So can we get an insight from Python layer also?
Yes, absolutely. You can see inside the Python layers what's happening, and even look at the interfaces to other runtimes, including CUDA and AMD ROCm and so on.
Okay, thank you.
Okay, are there any other questions? So if not, again, thanks Samir for the talk.